Howdy class. Last time we went over straight lines and some applications to straight lines. And so now we're going to take this a little bit further. We saw, supply and demand equations. Those were two different types of lines. And the intersection of those lines has a significant application in economics. So in this class we're going to go over specifically how to find what's called a solution to a system of linear equations, right? That would be two equations, two variables for now, and we are trying to find a set of x and y coordinates that satisfies both the equations. So like here you've got two equations, and we want to find the x and y that is a solution to this equation and a solution to that equation right there. So what we want to do here is we want to verify that the x and y coordinates 1 and 2 are solutions to this equation. So all we do is we plug 1 and 2 into the first equation to make sure the left-hand side equals the right-hand side. So we plug it in. Left-hand side equals 2 times 1 plus 3, which becomes 2 plus 6, which is 8, which is the same as the right-hand side. So it checks out. That is again for equation 1. Now let's look at equation 2. So we start off with the left-hand side equals 4 times 1 plus 5 times 2, and that equals 4 plus 10, which is 14, and the same as the right-hand side. So it is therefore a solution to both equation 1 and equation 2. And so here we have a graphical representation of what we're working with. The red line is the first equation, 2x plus 3y equals 8, and the blue line represents the second equation, 4x plus 5y equals 14. And as you can see, the point they have in common, that would be the solution to both equations, is right here, 1 and 2, which we found just recently. Now, in general, for a system of linear equations, we have a couple of different scenarios, right? We just saw the one where we've got one solution, but there could be an instance where we actually have no solutions, and let me go ahead and put one such case up here for you. Right? Parallel lines, right? No solution right there. That is, there is no x and y set of x and y coordinates that will solve the red line and the blue line simultaneously. The other setup would be this one. 2x plus 2y equals 8, 4x plus 4y equals 16. Two different equations, but note they share the same line, or the same graph, should I say. This would be an instance where there are an infinite number of solutions to the equation. So now back to the handout. We're going to try a way to find the solution called the substitution method. So the first thing we're going to do is we're going to solve equation 1 for y. So basically we have 3y equals 8 minus 2x, then divide everything by 3. Okay, so now that we've got a value for y from the equation 1, we go ahead and plug this into the other equation, like so. Alright. And then we solve for x. First step here is we're going to multiply both sides by 3. And then distribute the 5. Now combine like terms then subtract by 40, then divide by 2, getting you an answer of 1. Okay, so there we are. That is our x value. We are now going to use this x value to find the value of y. So we do this by plugging our value for x that we found right here into the other equation. And so we put that in right there. And now we solve for y. And we find that y equals 2. And so we've got our ordered pair set here. X and y equals 1 and 2. Which we've already verified earlier. Alright, so now we're going to do the same trick, the substitution method. We're going to go ahead and solve equation 2 for y. So we do this, we get y equals 7 minus 3x. And now let's come over here. We're going to take equation 1 and substitute in our y value from equation 2 so that we have 5x plus 2 times 7 minus 3x equals 12. So there is our substitution step right there. First thing we do is distribute that 2. And now we combine like terms, subtract the 14, and now we multiply both sides by -1 to find that x equals positive 2. Now all we got to do is plug in our value that we found for x into our value for equation 2. So we have y equals 7 minus 3 times 2. Work that through and you'll find that y equals 1. So our ordered pair are of x and y are 2 and 1. And you can check this ordered pair by substituting 2 and 1 into equation 1. And when you do that, you'll find that you get 5 times 2, which is 10, plus 2 times 1, which is 2. 10 times 2 is indeed 12. So yes, that does work. So let's go ahead and move on to the next bit here. Concept check. How many solutions does a system of equations describing parallel lines have? Well, we already graphed an example of this in Desmos, and of course a set of parallel lines will have 0 solutions, as they have 0 points in common. That is 0 points that solve both equations simultaneously. So now let's go ahead and look at a method called the elimination method. And so the goal here is to add equations together in such a way where we begin eliminating variables. So here we've got this system set up, and so we note that we can multiply (2x), that's the value here, by -3, and we'll get -6x. Add those two variables together and they will cancel each other out. So again, we'll be adding these together variable by constant. So first thing we do is we multiply equation 1 by -3, and we got -6 here, -6x, -15y, and over here we have -21. Okay, so now we add everything together term by term. Of course, we got a 0 times x, and then we've got right here a negative 8, and over here we have another negative 8. So now this means that we have the equation set up, negative 8y equals negative 8. So solving this for y, dividing both sides by negative 8, we find that y equals a positive 1. And so we plug this value into one of our original equations. So we got 2 times x plus 5 times 1, and that equals 7. So again, we're solving this equation for our x value. And so we get 2x equals 2, so x equals 1. And so our set of ordered pairs are 1 and 1. Let's go ahead to the next example here. We'll be using this very same technique. So here, note we're going to multiply this system here by negative 3 times equation 1. And so the system then becomes negative 3x minus 6y equals negative 15. And then the original equation 3x plus 10y equals 26. Okay, so we are adding these two equations together, and we have 0 plus 4y is 26. 11. Divide both sides by 4. And now we're going to take this value of y, plug it back into our equation 2. I'm sorry, we're going to plug it into equation 1. You could plug it into equation 2 as well, that would work, but we're going to do equation 1. So we have x plus 2 times 11 over 4, and that equals 5. Okay. So let's go ahead and get rid of this 4 in the bottom, and we're going to multiply both sides by 4, so we have 4x plus 11 equals 20. 2 times 11, sorry. And so we got 4x plus 22 equals 20. Subtract 22 from both sides, and we get 4x equals negative 2. Divide both sides by 4, and we find that x equals a negative 1/2. So our set of ordered pairs is negative 1/2 and 11 over 4. Okay. Moving on. Next equation, or next system of equations, we have this guy here. And we're going to have to multiply both equations this time. We're going to multiply the top equation, equation 1, by negative 2. And we're going to multiply the second equation by 5. And so this gives us, on the top, negative 10x plus negative 6y equals negative 42. And then the second one becomes 10x plus 2y equals 34. Adding these two equations together, we get 0 minus 4y is negative 8. Divide both sides by 4 to find that y is 2. So just like that, we got one of the numbers. Plug this into either one of the equations. We're going to do equation 1. So we have 5x plus 3 times 2 equals 21. Solving for x. All right, and then you divide both sides by 5 to find that x equals 3. Okay, so that's the number we're looking for. We have our set of ordered pair. X and y equals 3 and 2. And you can check that set of ordered pair by plugging them into this equation to make sure that the left-hand side does in fact equal the right-hand side. Alright, so this is all fine and dandy for equations in two variables, 2D space. Now we're going to look at moving into a three-dimensional space. This will include a third variable. And we're going to be using this website here to help us visualize the graphs that we're going to be looking at. So moving forward, let's go ahead and look at this first guy here. Alright, so you can see that we've inputted the equations right over here. Note that we did have to solve them for z in order to get them to plot in this graph. And so keep in mind, a solution is going to occur whenever all three of these planes intersect, and each plane represents one of the equations we are looking at. And as you can see, as we look through this, they have exactly 0 points in common with each other. So this tells us that there is no solution. But let's look at the equations again and verify this result. So we're going to use a substitution here. As you can see, z equals 3, so we're just going to plug that value in these other two equations so that we have x plus y minus 3, and we've got x plus y plus 3, right? And they each equal 0. And then move the 3 over in each case, add 3 to both sides here, so that we have x plus y equals positive 3, and then over here we have x plus y equals negative 3. Now if I add, or if I subtract these two equations from each other, I'll end up with the result that, right, 0 plus 0 on the left hand side equals 6 on the other side. 0 equals 6, right? That is an inconsistent system. There is no such solution as we saw graphically. So anytime we get something like this is a clear indicator that there is no solution. And that would be our answer for this question. Alright, let's go ahead and look at this guy right here now. Okay, once again, we've got all our equations solved for z and inputted over here. When we take a look at the three planes these guys create, we can see clearly that there is a single point of intersection that they all have in common, occurring right there by my mouse. So now let's use some algebra to uncover what that solution is that they all hold in common. So first off, let's go ahead and restate this in a way that we can kind of tell where things are just a little bit easier. And we're just going to put the variables right on top of each other. This way we see exactly what is going on. Okay, so what we're going to do here is we're going to add those two equations together. We're going to replace equation 2 with the sum of equation 1 and equation 2. So we've got equation 1 plus equation 2, and when you add these two together you get y equals 0. So now we're going to use this result, plug it into equation 3. So equation 3 is going to become negative 0 plus z equals 1. Right? Equation 3 right there. And so from this, clear enough, z equals 1. So now we're going to go back to equation 1 and substitute in what we now know. And when we do that, we've got x plus our y value, which we found to be 0, plus our minus our z value, which we found to be positive 1, and that all equals 0. Solve for x, and we find that x equals 1. Okay, so there we are. We've got our x, y, and z values. We have our ordered group of x, y, and z, and that's going to be 1, 0, and 1. Okay, so that was that coordinate that we saw where all the three planes intersected back in our graph over here. 1, 0, 1. That is that point right there that you see. Okay, now on to the next equation, or system of equations. Once again, we have these solved for z right in here, and when we look at the graph, we see that they've got not only one point in common, it's got a whole infinite number of points in common. All these points that lie along a straight line. So we need to figure out what this straight line looks like, what the equation that describes this straight line. Alright, so to find the equation of that line, first thing we're going to do is we're just going to add these two equations together, and that's going to get us, I'm sorry, not add, we're going to subtract them from each other. And so x minus x, that's 0, y minus 0, that's going to be y itself, and then z minus z will be 0. Or should I say negative z minus negative z is 0, and then of course 0 over 0 is 0, so we know that the y value, the solution will have a y value that is equal to 0. So let's plug this in to our equation 1 that does have a value for 0, for y. So we have x plus 0 minus z equals 0. And so from here you'll find that we have the result that x equals z. So we could describe this equation as the line through three-dimensional space x equals z such that y equals 0. Okay, and that would be a perfectly acceptable way to explain this. If we want to put this in terms of coordinates, we could write this as whatever x value is, y value is 0, and then the z value will take on whatever the x value is. Alright, and that describes that line through three-dimensional space. Let's move on to the next one, where we will look at this guy here. Alright, it wasn't until I looked at the graph here that I realized we'd actually already done this exact same system earlier in the paper, so worth taking a look at the intersection of all these three planes again. All these three planes have in common is this one single point made up of 3 coordinates. So we'll go ahead and skip doing this one twice since we already did it immediately above. So moving on over to this next one in line here. Let's go ahead and look at the graph of him. Okay, and as you can see, we have the equations inputted in, solve for z, and you can see there's going to be another line, right? A straight line through 3D space that we need to describe here. So now let's find the equation of that straight line. And so first thing we're going to do is we're going to take equation 1 and subtract equation 2 from it. And when we do that, we get, so again we're subtract, so right in there. And so when we do that, we get 2x plus 0 plus 0 equals 0. So that gives us the simplification that x equals 0. Now when you plug x equals 0 into any of these three equations, you're going to end up with the same results. You will see that equation 1 equals equation 2 equals equation 3 when x equals 0. Right, and so when we plug it in, what equation is that? That is simply y minus z equals 0. So we can get y and z in terms of each other. We'll see that z equals y. So 2 ways of writing this. We can write this as z equals y such that x equals 0, perfectly acceptable way to write that, or as a set of ordered pairs, 0, y, and y, right? Whatever value y is taking on, z will be taking on that same value, so long as x equals 0. Okay. So let's move on to this last one here. And so here we have the final set of equations of the handout. Gives us this looking guy here. And you can see that it has a point that satiates all 3 equations right there. So let's go ahead and find that using the algebra. Alright, so first thing we do, equation 1 minus equation 3. And when you do that, that is we've got equation 1 and we're subtracting out equation 3. Alright, so this will give us 0 plus y plus 0 equals negative 1. So y equals negative 1 is what we just found. Okay, that's pretty good. So we're going to plug that into equation 2. Solve for z. And now we've got a value for y and a value for z. So we can use both of these to find a value for x. And let's go ahead and use equation 3. So equation 3, we have x minus the value z has for at 1 equals 1. Solve for solve for x, and we find that x equals 2. So our set of ordered pairs x, y, z is 2, -1, and 1. All right. Okay, I think this is a good point to end the class out. We've gone over quite a bit of material. Make sure you review it thoroughly and that you are comfortable with it. And email me if you have any questions. And if I don't talk to you